Gerrit Schellenberger got his PhD early this year. Dr. Thomas about the clusters, and he also worked at and XMM. He was radio astronomy postdoc in. He's going to talk about some work he has done.
Hello everybody, I'm going to talk about the system that you can see already over here. To talk about here some merging events and AGI collaborating with Jan and Simona, who was doing in Maryland. Where we have, in our theory, we have a very smooth density field of the matter density distribution, and as time progresses, you can see in this simulation here, we have gravity acting on the matter and builds. So following this theory, we can actually predict the number density of these overdensities of these dark matter halos as a function of their mass, and that is shown on this plot over here. So we have the mass of these objects. So we have many more of those in the universe, so it's actually then obvious that they need residing in these galaxy groups and only very few in the clusters. So if you want to trace the and full understanding of the structure formation, how it was built up from galaxies, grow to galaxy groups and then to clusters, you need to understand how the distribution of galaxy groups actually as a function of their distance or redshift. So you can clearly see already certain filaments, much more than the high mass object, the galaxy clusters actually. How do the member galaxies actually influence the star formation in these galaxies, which are residing in the galaxy groups, in every of these member galaxies? And especially how important is the AGN in the famous example that all of you know and that will also be shown. It's the bullet cluster, and you have here the unique post-galaxy clusters, which is the hot gas in X-rays in red, and also the dark matter in blue, which is traced by Weak mergers. We can actually, we have to study, we have to see how they impact scaling, and furthermore, they are important to understand physics that are going on in these galaxy clusters. So when we have a galaxy cluster, we have a production of relativistic particles, and they will be context. For example, here you can see in this cluster Abel 3 over here and over here, but also the central put energy into the intracluster medium and space, and this is usually traced by the radio emission that you see in the contour. So all I want to motivate here is that the multi-wavelength in this context to understand these systems. Interaction process that one has to look at is falling into the galaxy cluster, and there create. It's a very luminous cluster, and also galaxy over here, which was formerly a field. Blue over here, this gas, this emission over that has been stripped off this galaxy. Case is special because it's one of the, and it's the first case that it has been the X-ray tail. So just here you see again in X-rays the gas that is detached from the galaxy over here. You can analyze, you can do you can trace the profile, the surface brightness, and you can look in the radio regime at this is the NBS, and the contours here in red is again the X-ray contours. So galaxy, and the red contours are these circles that are indicated here. You have some excess that would fit in this picture if it's bent upwards. So this would also match with the inferred direct talk about for the rest of the talk, NGC 741. It's, as I said, rays, but also radio, high resolution radio data and HST data. So here, this is the galaxy that we that is actually called NGC 740. There's another galaxy very close to it, which is called NGC 742. Out all the time the difference. So this is a much smaller galaxy, but also very close to the image that I have. It looks like this. So we have here this long radio tail. Here some, on smaller scales, some very intense objects. And now overlaying again strong X-ray emission here. It's I will show later some filament, X-ray filament down here, so that also these two objects. Brief overview of what has been done on this group before. There was a very early paper by Birkinshaw. Here again the big galaxy in the center, and this is the smaller one that you saw in the picture before. And the emission over here, which was the beginning of the long tail in the previous picture. Another paper just discovered these are radio contours again. You see the tail down here. And over here would be the claim for it was found that on the one hand, some scenarios could be made up. For example, the area could be filled with a very hot plasma. This fit to the picture that we didn't find, or they didn't find a high energy cutoff in the radio spectrum. So in the end, in the past, there were these 30 kilos. Over here is actually from the XMM data that we have, the clean observation time. And possibly we can add some of the important constraints that I will show you in the end. Plus this, so let's look at the galaxy group in total. We have here a temperature profile. So the temperature of the system is around 1.5, 1.4 keV. And you also see that here data agree quite well, and also the XMM data agrees well. And this is actually expected because the cross-calibration problems that are known for these two objects only matter in the higher temperature regime, so not at these lower temperatures. We can also see that the peak temperature is around size. Let's now look at the spatial distribution of the temperature. So this is a temperature map of the object. So we see here in the center, the blue part is, and the contours in black that you see here, they correspond to the X-ray surface brightness. So here you can see that the cool gas is going into this direction. So filled with the cool gas, which is probably actually stripped gas from this galaxy over, which we of course, since we just have, the object is so nearby and we have just a small part of the total, same approach that I use for the high flux clusters. So we get a total mass of around 3.5 10 to 13 solar masses, it should say here, systems. So let's go to the surface brightness that we see in the central galaxy, and this is the smaller one more to the east. So you see the filament to characterize the overall cluster emission. We also see this excess to the north over here, where this is coming from. So this still needs to be studied further. But the filament over here, that is looking at the surface brightness profiles, centering on the main galaxy and going into different, this excess to the north over here as this bump in the surface brightness profile over here to decrease the steepest drop in the spectrum, in the profile of that object. Here's again the surface brightness distribution, and some regions trace the filament that we measure, like the surrounding medium of the filament. So here with its temperature, and these are 1 and 2 sigma contours. So it has roughly a similar composition, but it's at much cooler temperatures. With this, the structure that we see here to the north, it also has a cooler temperature as much as the filament over here. Also, since we have the spectral information, so temperatures, abundance is usually a useful quantity to characterize the gas pumping or things like that. So this is not a profile, so users. So starting with this one over here, that is what you see in blue, in the blue circle over here. The ring over here, that is just the increase if you go to larger radii. But the same radius as the ring has a much lower entropy, stripped gas from the galaxy. Furthermore, we can the other publication that found it is actually lower than the ring that we have here. So we still need to investigate this brightness. but maybe with the entropy we can get an idea. Then go to the radio regime. We have here the emission that connects the two. So now I'm going to range from 160 megahertz to the smaller part that connects these two. So we have here this VLA and trace basically the direction that this galaxy was moving. But we also see that the X-ray filaments, one needs to consider that these two came from different processes. So the X-ray filaments, they are stripped gas, and the other ones are the radio trace for a galaxy on the tail to the south. This is a region further away. And ignoring this drop here at the very low frequencies for a moment, we can see that it follows, stood as a spectral aging. Since the high energy electrons lose their energy first, we have the tail, and here are the two galaxies again. We see that the steepens along the tail, and we can calculate if we assume an overall. We also see that in this region, which is in blue, we have no deviations from a power law. So this is probably still powered by the AGN of 741. Assuming a power law distribution for the electrons, we have a spectrum which also follows a power law. But we cannot differentiate between these two cases, but we can estimate an age from this cutoff, or this characteristic frequency itself. So this is an integrated radio spectrum. So the whole radio tail, we can see that it follows overall a power law with an index of 1, absorption. So what happens is that the electrons that produce the synchrotron emission, thermal emission, it's not a black body, but it again follows a power law with an index of 2.5. Immediately this 2.5. Nevertheless, this 2.5 was up to now, to my knowledge, never observed before, involved in this system. Plus, you can also learn something on the source itself. And so here you see the HST at 500, that it has some rings or something is disturbed in the image using a Sersig model, and you can clearly see the ring underwent before some interaction, even has interacted or captured a smaller galaxy over in the radio. From down here with a very high velocity, and the big galaxy was here, and they both encountered each other with this AGN emission. Over here we have the X-ray filaments, which is mostly the stripped gas from a 7th galaxy, the gas content that would be expected for a galaxy like this. We have here to the north, which I mentioned, entirely connected to this interaction. It could have been from a previous merging event. Or mainly we can see it here in the broader radio image picture. I will end my talk, and thank you for your attention.
So that X-ray payloads in the galaxy, right? How do you know they're connected?
So this is clearly spectroscopically confirmed a member galaxy. There is not a background group or something, but this is in this. Plus, there is nothing else in there which could cause that. So a huge galaxy, so it's the only one that could produce this tail in there. We need a longer observation to definitely confirm that there is a connection or something like that. We didn't see that. That is just, I think, like 10 kiloseconds observation. Maybe even discover a bow shock or something like that.
Extra observation itself at all, like this galaxy?
This galaxy?
Because it's disconnected.
Oh, yes. No, we didn't observe anything in there.
Totally, yes.
So at your very, very last slide, you have velocity high enough that you should see a shock somewhere. You know what its velocity is on its way out now?
And the projected distance.
Okay.
So that is really a very rough number. I think the sound speed. No. No.
As evidence of that in front of it going on the way out anymore.
No, we didn't see anything there. No.
Graph that was like it's temperature versus radius, correct?
Yes?
And if you could go back to that, it peaks at over 2 keV. Have there been any
quite high. It could be in this regime where maybe there, I mean, we didn't see a map. So it's not completely clear to us why it's peaking so high, but it could also be that these are just some outcorrect. Yes.
Where they asked a big shock in the second part, and they like have radio diffuse emission of gas clusters. And she did some research at the University of Maryland and observations of gas clusters, and she's spending a very and today she's going to talk about her work here.
Thank you very much for the introduction, and thank you all for being here. I did in two main parts. In the first part, I will briefly introduce you the diffuse radio emission from galaxy clusters, and then I will focus on radio halos, and I will present you the state of the art, both from an observational and a theoretical point of view. And then I will focus on recent results on the dependence of the fractional cluster with radio halos on the mass of the clusters, and also on the radio halo merger connection. Then, on the second part of the talk, I will show you which are the open issues that affect mainly this first topic here, and I will also tell you what I've been doing for the past few months here at CFA, and I will show you very new and preliminary results that we obtained so far. So, some galaxy clusters show diffuse radio emissions that can be in form of radio halos, relic, or mini halos. All these sources are not magnetic fields mixed with the intracluster medium. So relics and radio halos are found in merging systems, and relics have these shock fronts. Radio halos instead are centered on the center of the X-ray emission of the cluster, and their morphology usually follows the X-ray morphology of the cluster. So as I told you, I will focus on radio halos. As the name suggests, are smaller structures, and they are typically found in relaxed clusters, cool core clusters. So the main problem that arises when explaining the origin of radio halos is the fact that the diffusion time needed to the electrons to cover the megaparsec scale is much larger than their radiative lifetime. So this is known as the diffusion problem, and it requires some mechanism of acceleration or injection of particles in situ, directly on the megaparsec scale. So there are two main classes of models that have been proposed to solve this issue. According to secondary models, the radio-emitting electrons are continuously produced in the ICM via proton-proton collisions between thermal protons in the ICM and cosmic ray protons. But nowadays, this model is disfavored by a number of observational evidences. And what we think is happening is that the radio-emitting electrons are reaccelerated by turbulence injected in the intracluster medium during merger events. So in this context, in the turbulent acceleration scenario, we can derive a basic prediction about the statistical properties of radio halos. So let's start from the formation of galaxy clusters. In the hierarchical view, galaxy clusters form via subsequent mergers of smaller substructures. And at each of these mergers, some turbulence is injected in the ICM. And this turbulence reaccelerates electrons with an electron acceleration coefficient which is directly proportional to the energetics of the merger, which means that it is directly proportional to the mass of the clusters involved. So the first prediction is that radio halo forms with different spectra, and in particular with different Bragg frequency. And the Bragg frequency is proportional to the electron acceleration coefficient. So what does that mean? That means that massive systems undergoing energetic merger events are thought to form radio halos with high noise. And when you observe at gigahertz frequency, you expect to find an increasing fraction of clusters with radio halos with increasing the mass of the clusters. But there are also less massive systems undergoing less energetic merger events that form radio halos with very steep spectra, the so-called ultra-steep spectrum radio halos. And because of the presence of the ultra-steep spectrum radio halos, when you observe at low observational frequency, you expect to find an increasing fractional cluster with radio halos. Now, I'm sure you understand that we need large samples of galaxy clusters in order to test this expectation. And we would like to have mass-selected samples of galaxy clusters because the mass is the key parameter of the model. The first big step forward in this sense has been made through the Gerrit radio halo survey, which is an X-ray selected sample of galaxy clusters, but you know that there is a correlation between the X-ray luminosity and the mass of the clusters. So thanks to the Gerrit radio halo survey, it has been discovered that galaxy clusters have a bimodal behavior in the radio power X-ray luminosity diagram, with radio halos that lie on the correlation, and non-radio halo clusters that you see here as upper limits are well below the correlation. Moreover, radio halo clusters are merging systems, while non-radio halo clusters are relaxed. Another very important achievement that has been found with the Gerrit radio halo survey is the index of about 1.8. And let me stress that this was a very important discovery because it was one of the main rule out the secondary models for the formation of radio halos. So what's new now? So recently, the Planck satellite has surveyed the sky via the Sunyaev-Zeldovich effect, which is a very robust indicator of the mass of the clusters. Because again, there is a correlation between the SZ signal and the mass of the clusters, but it's much higher than the one with the X-ray luminosity, and it doesn't suffer from biases introduced, for example, because of the presence of cool core clusters. So from now on, I will talk about a mass-selected sample of galaxy clusters, even though I should say an SZ-selected sample. But nowadays, an SZ-selected sample of galaxy clusters is as close as possible to be a mass-selected sample. So our first aim was to measure the fractional cluster with radio halos and its dependence of the cluster mass in a mass-selected sample of galaxy clusters, and also to continue the study of the connection between the presence of the radio halo and the dynamically disturbed status of the cluster. So we selected from the Planck catalog those clusters with mass greater than 6 times 10 to the 14 solar masses in this redshift range. And we collected in this way a total sample of 75 clusters. And we then searched for the diffuse emission in the MVSS for low redshift clusters and in the extended Gerrit radio halo survey for high redshift ones. So for high redshift clusters, we found information on the Gerrit radio halo survey for 36 clusters. For the low redshift sample, we have a lot of information in the literature, but we also had some clusters that didn't have any deep radio observation. And for those clusters, we reprocessed the NVSS dataset in order to lower the RMS noise and have at least an idea of the possible presence of diffuse emission. So we had, I need to plug in, so but I can continue talking anyway. So we ended up having these 4 cases that still need confirmation about the presence of the radio halo. Thank you. Okay. And now I will talk about this subsample of clusters, of 57 clusters that have available radio information and that constitute a sample with mass completeness of about 67%. I think there's something over here. Okay, sorry about that. So let me go to the result. We have 57 clusters. Yes, 57 clusters and 24 Oster radio halo. So we want to see how the fractional cluster with radio halos depends on the mass of the clusters. So we split the sample into 2 mass bins, the high mass bin and the low mass bin, and we measure the fractional clusters with radio halos separately in the 2 bins, finding that the fraction of radio halos in the high mass bin is about 80%, while it is about 30% in the low mass bin. So we measure for the first time the presence of a drop in the fractional cluster with radio halos at lower masses in a mass-selected sample of galaxy clusters. And we also tested the statistical significance of this result using Monte Carlo simulations. So in particular, we randomly assigned 24 radio halos among 57 clusters, and we counted the number of radio halos falling, for instance, in the high mass bin. So here you see the distribution of the number of radio halos in the high mass bin after 10,000 Monte Carlo runs. It can be fitted with the Gaussian function. And what we want to see here is how far the observed number of radio halos is in terms of sigma from the most probable value that is predicted by the Monte Carlo simulation. So we found that our observed number of radio halos is at 3.2 sigma times from the value that we should observe if radio halos were distributed randomly, independently on the cluster mass. And this means that the probability to observe by chance this number of radio halos is less than 10 to the minus 4. So our results with the expectation of the turbulent acceleration model that you see here as a red line and shadowed region. Still, also the model is in its very basic form, but you can see that there is quite a good agreement between the observational result and the expectations of the model. So the great majority of the clusters also have Chandra X-ray data that we reduced, and we analyzed the X-ray surface brightness inside 1 megaparsec aperture in order to derive these two morphological parameters, the concentration parameter and the centroid shift. The concentration parameter is a measure of the X-ray, the ratio between the X-ray surface brightness inside the core of the cluster and inside the wall aperture. So high values of C mean that the cluster is relaxed. The centroid shift instead is a measure of the shift, or the distance between the peak and the centroid of the X-ray surface brightness. So high values of W mean that the cluster is dynamically disturbed. Here you see the CW morphological diagram, where relaxed clusters can be well separated from merging clusters. But what I want you to note here is that radio halo clusters, the red dot, are emerging systems, while no radio halo clusters, the black dots, are in the relaxed region of the diagram. So we confirmed again that radio halos are hosted by merging clusters, while those clusters that do not have radio halos are usually more relaxed. So let me conclude this first part, summarizing the main points. So we measure for the first time a drop in the fractional cluster with radio halos at low massive systems, and we estimate that this is a 3.2 sigma result with Monte Carlo simulations. We started to compare this result with the expectation of the turbulent acceleration model, finding a good agreement. And we also confirmed that radio halo clusters are merging systems, while no radio halo clusters are relaxed. Now, you might remember this slide where I've tried to explain you how many clusters we've actually used to achieve this result. And I'm sure you understand that we have two main issues here. The first one concerns the high redshift sample, because we still didn't have deep radio observation for 18 clusters. So we asked and obtained time at GEM-RT at 610 MHz for all these clusters, and also at JVLA at 1.5 GHz for 10 of them. The second issue instead regards the low redshift sample, because we have this cluster that suspect diffuse emission in the MVSS but still need confirmation. So we asked again and obtained GEM-RT 330 MHz observation and JVLA 1.5 GHz observation, and all this analysis is in progress. So adding this new data to the sample that we have already published will give us a big sample of 75 galaxy clusters in this mass and redshift range, which will be more than 80% complete in mass, and all these clusters will have deep radio observations. So the data analysis of all this new data is the main core, let's say the core of my PhD project, and actually the JVLA data analysis is the main focus of my visit here at CFA. So let's move to the second part. We have JVLA 1.5 GHz observation in C array for 10 high redshift clusters. And we also have one archival observation for this high redshift cluster here. And also we have, again, 1.5 GHz observation in D array for the 4 low redshift interesting clusters, let's say. So we are talking about D and C array observations because they are all low resolution observation, because that is what we need in order to be sensitive to diffuse emission in galaxy clusters. So I don't have time to show you everything, but I would like to focus on these two galaxy clusters that are particularly interesting, at least among the ones that we have already analyzed. So Abel 1443 is an high redshift cluster, a massive cluster, and it's a merging system. You can see here the CW morphological diagram and its position already. It's really, we have tried to produce images at lower resolution. We did several tests, but the radio halo is only marginalized the archival JVLA 1.5 gigahertz observation of this cluster. And we have both D-array and C-array observation. Let me say just once that all the analysis, the calibration, the imaging, everything of JVLA data is performed with CASA version 4.6. So this is the final image obtained by combining the C and D array. A bright radio halo, I agree, and this again suggests the possibility of a very steep megahertz and 1.5 gigahertz with two different telescopes. And believe me that we have tried this where point sources have been subtracted, but you see that this source in the 330 megahertz is not completely subtracted, the flux coming from this source. And these are the results. So for about 40, and this gives a spectral index of 1.9, which is 1.2, 1.3. So this is indeed an ultra-steep spectrum radio halo. And what is next for this week? And also we are going to observe it with LOFAR in the next couple of months. So the second cluster that I would like to show you is a low redshift cluster. It might be less interesting than the Abel 1443, but it's interesting to me because it was one of those clusters for which I reprocessed the NVSS dataset during my master's degree thesis, and here you see the white contours are the NVSS. And I pointed it out as a probable radio halo. So we asked for GMRT 330 MHz observation and for JVLA 1.5 GHz observation. We analyzed the JVLA the sources, and here the sources are subtracted. Now, I'm not at the peak of the radio halo, actually, but you know that D-array observation are very good for vision. So we are now going to analyze B-array, Raynaud's B-array point source, and in case it is a point source, we will be able to properly subtract it and have a cluster. So we will also have nice information about the spectral index. The fractional cluster with radio halos drops in low massive systems. And the second message is that we have a bunch of new radio data of galaxy clusters, and we are finding interesting results, like the cluster that I've just shown you with a new radio halo, and also, in particular, the Abel 1443 that hosts an ultra-steep spectrum radio halo. And let me stress again that ultra-steep spectrum radio halos are very important because they are uniquely expected in the framework of the turbulent acceleration model, and also because their existence means that at low observational frequency with future telescopes, but also with present observation, we will be able to find an incredible number of new radio halos that we are not seeing now because we are observing in a higher frequency range. And let me conclude with this wonderful picture of Boston downtown.
The fact that you don't observe many clusters, low mass clusters, current radio instruments.
Of course it is. Well, yes. This is what I would like to show you. So yes, I mean, of course there are very low mass systems that are here for which we can't tell anything right now because we don't have enough sensitivity in our radio observation. But in this mass range, the presence of the upper limits tells you that actually if you have 0.4 gigahertz have very low